Our speaker today is also one of our new Circus Fellows, Ariel Procaccia, who works in interface between social choice theory, AI, theoretical computer science, and economics, if I haven't missed anything. We are very excited to have him here. His work has already received a lot of recognition. His dissertation in computational social choice theory has received awards from the International Federation of Autonomous Agents and Multi-Agent Systems and Hebrew University. And today he'll be telling us a little bit about his research. Welcome, Ariel.
Thanks, Salil. Okay, so the title of this talk is f of x marks the spot. And so I don't want to, I'm trying to take a slightly different approach with this talk, so I don't want to give you an outline of the talk and to do things more formally, because I think the topic is very intuitive. So I'll sort of try to do everything informally and give you proofs by animations, and then smoothly slide into the results. So the question I want to start with is where to locate a library on a street. So let's say we have the street and we want to locate a public facility like a library or a train station. And we have a set of n agents that I'll denote by letters A, B, C. And each agent reports its ideal location. So the assumption is that each agent has an ideal location for the library. One agent might it to be close to his home because he likes to read books in his spare time. Another agent might want it to be close to his workplace. But each one of them has some ideal location. Now, a mechanism is a function that receives as input the ideal locations of the agents and outputs the location of the facility. Okay, so it maps these locations reported by the agents to the selected location of the facility. Now, given the facility location that was chosen by the mechanism, the cost of an agent is his distance from the facility, the distance between the facility and his ideal location. Okay, so in other words, we have a measure of unhappiness of an agent, or disutility. So the agent is unhappier the further away the facility is from his own location. And specifically, the unhappiness is exactly the distance between himself and the facility location. So that's the agent's cost. Okay, so let me give you a first trivial example of a mechanism. So our street is going to be this street, 57th Street. The colors are a bit off, I have to say. Is there any way to tune the colors? Okay, so we'll make do with this. Yeah, they should look like Google Maps. So does anyone recognize the city here? Yeah, so it's New York City. You can see Central Park here in the north, and this is 57th Street. Now we're going to have just two agents in this example, A and B. And these are their ideal locations. So A wants the facility to be near the intersection with 9th Avenue, and B wants the facility to be on the intersection with 7th Avenue. Or is it, 7th Avenue. Okay, so these are the ideal locations of the agents. Now our mechanism works as follows. Given the ideal locations of the agents, we take the average or the midpoint between them. Okay, so if these are the two ideal locations, I put the facility in the midpoint between the two agents. Now, a game-theoretic property that I would like a mechanism to satisfy is called strategy-proofness. So a mechanism is strategy-proof if agents cannot benefit from lying. Or in other words, if an agent misreports its ideal location, the location of the mechanism from its real ideal location cannot decrease. Okay, so I cannot get the facility to be closer to my real location by lying about my location. And this midpoint mechanism, this average mechanism, is clearly not strategy-proof. Okay, so in order to see this, let's think about agent B. Let's say agent B is trying to lie in order to improve the outcome for himself. So what agent B can do is it can pull its reported location, let's say somewhere to the right. And as it pulls its location, it's pulling the location of the facility with it. In particular, if agent B reports a location that's twice as far from A, it can get the midpoint, the location of the facility, to be exactly on his relocation. Right? So B definitely gained from this lie. Now his cost is 0. The facility is now exactly on his relocation, on the original location. Right? So this simple mechanism, the average, the midpoint, is not strategy-proof. So let's take another example, the leftmost location mechanism. So first of all, I want to abstract away New York and the street. I just want to talk about agents located on the real line. Okay, so each agent has some location on the real line. It's an infinite street. And in this example, we're going to have 5 agents, A, B, C, D, and E. And so here's another very simple mechanism. Whatever the agents report, the facility location is going to be the location of the leftmost agent. Okay, the leftmost location reported by any of the agents. So in this example, the facility is located on the location of agent A. He's the leftmost guy. And the facility is going to be denoted by these revolving crosshairs. Now this mechanism, this very simple mechanism, is strategy proof. Right? So let's try to see why this is true. So let's say agent B is trying to lie. Okay, just to get some intuition. If agent B reports any location to the right of his relocation, nothing changes. The leftmost reported location is still the same guy. Right? So you can lie and say, I'm actually somewhere to the right, but then the outcome of the mechanism wouldn't be affected. Another thing you can do is you can lie and say, I'm somewhere to the left. Now, as long as he doesn't pass agent A, nothing changes. A is still the leftmost guy. But when he passes A, he becomes the leftmost reported location. Right? So he can affect the outcome of the mechanism by reporting a location somewhere to the left. But in doing this, he's only pushing the facility location away from his relocation. Right? So he managed to affect the outcome, but now the facility is further away from his relocation than what it was before. And this is true for any of the agents. Okay, so the only way agents can affect the outcome of the mechanism is by pushing the facility away from the relocation. Now, an even stronger property that we would like to see in mechanisms, a game-theoretic property, is called group strategy proofness. So group strategy proofness means that even a coalition of agents cannot all benefit from lying. Or in other words, if you have a coalition and everybody lies together, there's one agent whose cost does not decrease. Okay, one of the agents does not gain from the lie, one of the agents in the coalition. And then that member of the coalition wouldn't want to participate in this lie, wouldn't want to participate in the deviation. Okay, so I want to make sure that for any coalition and for any lie of the coalition, at least one of the members of the coalition doesn't gain from the lie. And you can actually verify that this mechanism, the leftmost reported location mechanism, is group strategy proof. So even if you have a coalition of agents, yeah, question. Yeah. So the whole analysis is sort of worst case analysis. So you would say even if the deviators have full information, they still cannot gain. Okay, so this is the game theoretical assumption called, so you want truthfulness in dominant strategies. Okay, that whatever you do, you cannot benefit from lying. You want the truth to be a dominant strategy. Okay, so even if you have completely full information, you cannot benefit. Okay, so this mechanism is group strategy proof by the same intuition. Even if you have a coalition of agents, the only way they can affect the outcome is by pushing it further to the left, away from everybody. So this mechanism seems like a good idea in terms of its game theoretic properties, but I think intuitively there's something very, very wrong with this mechanism. Right? You might have a situation where you have one guy somewhere to the left, and all the other million agents are located somewhere to the right. And the mechanism will choose the location of the one loner instead of all the other guys who agree on the same place. Right? So there's something intuitively wrong, and let me try to formalize this. Okay, let me try to formalize what's wrong about the mechanism. So let's define the social cost of a facility location to be the sum of costs of the agents, or the sum of distances between the facility and the locations of the agents. Now, like I said, the leftmost location mechanism can be very bad in terms of the social cost. Okay, so let's see a specific, an explicit example. So let's say we have one agent located at x equals 0, and all the other agents, all the other n-1 agents are located at x equals 1. Now, the mechanism would select the leftmost location, which is 0. Right? And then the social cost of the mechanism that I denote by mech would be n-1. So we pay the distance between 0 and 1 for each one of the n-1 agents that are located at 1. Right? So the social cost would be n-1. On the other hand, the optimal solution would select x equals 1 as the location for the facility. And then the social cost of the optimal solution, which I denote by opt, would be 1. We just have to pay the distance once between x equals 1 and x equals 0 for the one loner that's located at x equals 0. Okay, so here's the second and last real definition in the talk. So we had strategy proofness. This is the second definition, a very important one. So we say that the mechanism gives an alpha approximation ratio if for every instance the ratio between the cost of the mechanism and the optimal cost is at most alpha. Okay, so this is the standard definition from approximation algorithms. We just want to say the mechanism can be at most alpha times as bad as the optimal solution. And what this example shows is that the leftmost location mechanism has a very bad approximation ratio. Right? On this instance, on this example, the ratio was n minus 1. So the approximation ratio can only be worse than that. It's a worst case notion. Right? So the approximation ratio of this mechanism is at least n minus 1, very bad, scales very badly with the number of agents. So let's make another attempt. Okay, take 3. So we'll try another mechanism, maybe slightly less obvious, the median mechanism. So the median mechanism simply selects the median out of the reported locations. So if we have 5 agents in the example, we would select the third guy from the left or the third guy from the right. It's the same thing. So in the example, it would be agent C. Now, the median mechanism is, again, group strategy proof, and the intuition is the same as the leftmost location mechanism. So again, let me give you an example, some hand waving. So let's say agent D is trying to lie. The only way it can affect the outcome of the mechanism is by pulling to the left, by reporting a location to the left. Once he passes C, he becomes the median, but the only thing he's doing is pushing the facility away from his relocation. Okay, so it's, again, the same intuition. An agent cannot benefit from lying. Now, I think more interestingly, the median minimizes the social cost. So the median is the optimal mechanism in terms of minimizing the social cost. In order to see this, let's do the following thing. So I want to compare the median to some other facility location, to some competing facility location. And let's say the other location is somewhere to the left. Okay, so I want to compare it to another facility location to the left. And what I'm going to do is I'm going to smoothly move the facility between the median and this other location. Okay, so as I start moving the facility, I'm getting further away from 3 of the agents and closer to 2, closer only to A and B. Now, when the facility passes B, right, so I'm now getting further away from 4 of the agents and closer only to 1. By the way, there are some sound effects here, so I hope you can hear them. Yeah, hardly. Okay, and at this point, I'm getting further away from all 5 agents and closer to none. But the point is that in every stage, I'm getting further away from a majority of agents and closer by the same distance to a minority of agents. So in terms of the sum of distances from the agents, it's only getting worse and worse. Right? I'm only increasing the sum of distances or the social cost. So this is basically a hand-waving proof that the median is the optimal mechanism in terms of, it always gives the solution that minimizes the social cost. So by the way, so far I haven't said anything new. All this has been known in social choice, and I won't say anything new, I think, in the next 3 slides, and then it will start getting new. But basically, the new thing that I said here was the introduction of the concept of approximation into the setting, and we'll see later how it plays a bigger role. But what we saw so far is that if we are on a line and we're interested in the social cost, we have a perfect mechanism. It's in terms of the 2 desirable properties that we defined. So it minimizes the social cost, and it's group strategy proof. So not even a coalition of agents cannot benefit from lying. Any questions up to this point? Yes, a little.
Is this mechanism actually used?
Yeah, I can't think of any example in real life. I guess it is used. So for example, think of a political setting. So I think it's sort of, I would say it's implicitly used. So think of a political setting where the political parties are located on the line from left wing to right wing. Right now, so this is actually a pretty common interpretation of this kind of preferences on the line. And now you want to be as good as possible to the people in the country, right? So you want to be as close as possible to their opinions on this left wing to right wing line. And then what you would, one of the things that you can deduce from this result is that being a party that's on the median is sort of best for you. So the parties would try to locate themselves around the median. If you have many, so it's not in the US where you have 2 parties, but in Israel where you have 20 parties or 30. So you actually see a phenomenon of parties trying to center themselves around the median or the center. So I can't think of an example where it's explicitly used, but it's definitely implicitly used in the reasoning that people make. Okay, so what I want to do now is make things more interesting. So instead of talking about a situation where the agents are located on a line, let's suppose that the agents are located on a network. So we have a network that's represented as a graph. Okay, so now the agents are located on a network. For example, the obvious generalization would be, instead of looking at a road, we have a network of roads, and we want to locate, again, a public facility like a library or a train station. Another more computer science example is a telecommunications network. And then we want to locate a router or a hub. And you probably know more about networks than I do, many of you. But you can think of many examples for the public facility. And this motivates looking at specific network topologies, a line like we talked about so far, hierarchical network, which is basically a tree, or a ring network, which is basically a circle. Okay, so these are specific popular network topologies. Another example, which I think is amusing, so you can think of the network, instead of being a physical network, as being a virtual network. For example, think of the network as being the face of a 24-hour clock, and the facility is some daily task that we want to schedule, like a daily backup. Right? So each agent has a favorite time for the daily backup, and we want to find a time that's good for everyone. Right? So the agents are located on the circle, which is the hours of the day, and each one has a favorite time. We want to choose a time that's good for everybody. The first thing I want to show you in this more general network setting is that if the network is a tree, then what we said so far basically also works. Yeah, question?
One question is in the last example especially. There was an implicit assumption previously with walking that essentially the further you walk, the worse it is in sort of linear increasing scale.
Yeah.
Whereas it's definitely not true for scheduling something like a backup, where 5 to 6 might be fine, 601 is horrible, and 7 to 8 is fine again.
Yeah, you're absolutely right. So I completely agree this example is weaker. I guess I think I was trying to make the point that the network can be virtual. But you're absolutely right that maybe, so I guess if all the agents are sort of clustered around similar, so we say it can be anything between 5 and 7, nobody has any constraints, but you have specific preferences for the time, then it makes more sense. But I absolutely agree. The point was that the network can be virtual instead of physical. Okay, so I want to convince you that if the network is a tree, the same intuitions that we talked about, the median and so on, also work in this setting. So here we have an example. You can see that the agents are also located on the edges of the graph. So this is maybe a slightly different continuous model of graphs where each edge has a length, and an agent can be located anywhere on the length of the edge. So if the edge is of length 5, you can be located at the distance of 2 from one side and 3 from the other side. And here's the mechanism, which is a pretty intuitive generalization of the median mechanism. So what we do is we start from the root of the tree, and we move downwards in the tree as long as we can move towards a majority of agents. If we can't do that anymore, we stop. Right? So in this example, we would start, so we start from the root of the tree. The majority of agents is in the middle subtree of the root. So we start moving in that direction. We're getting further away from 2 agents and closer to 5. At this point, we can move to the left subtree and get closer to a majority still. Right, so we continue in this direction. We're getting further away from 3 agents and closer to 4. Now, once we reach the location of D, we can't proceed while getting closer to a majority of agents. So we stop here and return D as the location of the facility. Yeah, so exactly. So we move, yeah, exactly. Okay, so first of all, I think intuitively, the mechanism minimizes the social cost by the same intuition that we saw from the median. If you want to move from this point to any other point, you would have to get further away from a majority of agents and closer to a minority of agents. Okay, so this also minimizes the social cost on a tree. This mechanism is also group strategy proof. So again, just to see an intuition, let's say agent F is trying to lie about his location. If he reports any location in the same subtree, nothing changes. It doesn't affect the outcome. He can affect the outcome by pushing beyond D. And in that case, he carries the facility with him, but only to a certain point. Beyond this point, the outcome would again not change. Okay, so again, the only thing F can do is push the facility away from his relocation. And this is true for any of the agents, for coalitions, and so on. Okay, so if we have a tree, we're in good shape. We again have this optimal mechanism, which is group strategy proof. So in general, basically you can think of in this model, since the agents can always be located on the edges, and then it wouldn't be true if all the agents are on the edges. So, for example, in this example, the unique optimal solution is the location of D, who is not on a vertex. Okay, the unique solution in terms of the social cost. However, but you can think of it of an equivalent. You can think of the regular graph model. Okay, so if you feel more convenient with it, the same results, everything that I say in this talk, would also work for the traditional graph model, where you have a graph and the agents can only be located on the edge, on the vertices, and the distance is the number of edges. Okay, and then it would be true. Andrew? So that's a good question. So if the number of agents is odd, yes. So it doesn't matter what the root is. If the number of agents is even, no. So in general, if the number of agents is even, the median is also not completely well defined. So on the line, you can always talk about the left median. On a tree, you would have to say this is a rooted tree, and then you would end up in one of the two medians. But it's definitely possible to tweak it in a way that this doesn't cause a problem. Okay, but in general, if you have, it's true that the way I formulated the mechanism, if you have an even number of agents, the outcome would depend on which root you started from. Okay, so I guess the natural question at this point is what happens if instead of a tree, we have a general network? And there's a beautiful paper by Schumer and Vora that talks about this setting. So they basically talk about exactly the same setting as we do, or I guess we talk about the exact setting that they do. So they have a paper in JET 2004, Journal of Economic Theory, and they characterize the strategy-proof mechanisms in this setting. Okay, so I don't want to give you the exact characterization, but you can get the following corollary as an immediate result, that if the network contains a cycle, if it's not a tree, then any strategy-proof mechanism cannot give an approximation ratio better than n-1, better than the almost trivial thing. Okay, so in a general network, if you want a deterministic mechanism and strategy proofness, you can do better than a really, really bad approximation ratio. So this is the last thing that I'm saying that's not new. From this point, everything is new. Okay, so what I want to convince you is that if you allow me to use randomization, I can circumvent this impossibility result. Using randomization, I can do much, much better. So what do I mean by randomization? So a randomized mechanism is similar to what we talked about so far. It receives as input the reported locations of the agents, but now it can output a distribution over locations. So instead of saying I'm choosing this place as the facility location, I can say I choose this place with probability 1/3 and this place with probability 2/3. Okay, so I can randomize over the locations of the facility. Now let's define the cost of an agent to be his expected distance from the facility. Right now we have randomization. And the social cost is now going to be, like before, the sum of costs, which in this setting is going to be the sum of expected distances, or the expected sum of distances. It's the same thing. So here's a completely trivial random mechanism. We call it the random dictator mechanism. So what you do is you select an agent uniformly at random. You get the reported locations. You select an agent uniformly at random, and you return its ideal location. Now, this concept of dictatorship is a very common one in social choice. Usually it has a bad connotation. So the dictator is someone who gets what he wants no matter what the other agents want. Okay, so usually it's negative. This mechanism may be more fair in the sense that anybody can be the dictator with equal probability. Okay, so once someone is the dictator, it's unfair, but anybody can be the dictator. So here's a theorem about this very simple mechanism. This random dictator mechanism is strategy proof and gives a 2 minus 2 over n, where n is the number of agents, approximation for the social cost on any network. Now, the strategy proofness part should be pretty obvious. So let's say I lied about my location. If I was chosen as the dictator, then I obviously lost, because I could have got my ideal location. Instead, I got some misreported location. If I wasn't chosen as the dictator, nobody cares what I said, right? So it doesn't matter what I said. So I can't benefit from lying. Now, the approximation ratio is also pretty easy to prove, but you have to work a bit harder, and I won't give you the proof. Okay, so this mechanism, I guess, gives a sort of proof of concept that using randomization you can do much, much better than deterministically. You can get this good approximation ratio while maintaining strategy proofness. So what I want to do in the next 2 slides is discuss the group strategy proofness of this mechanism. Okay, I want to ask whether this mechanism is also group strategy proof. Okay? Can coalition of agents benefit from lying? So this example shows that if I choose a random dictator, in general, it wouldn't be group strategy proof. So this is a specific graph. That's basically a star with 3 arms of length 1. And we have 3 agents located at the leaves of this tree, okay, at the leaves of the star. Now, the random dictator mechanism is going to choose each one of the agents with probability 1/3. Right? We're choosing each one of the ideal locations with probability 1 over n. We have 3 agents, 1/3. What's the expected cost of an agent? What's the expected distance? So everything is symmetric. Let's look at agent A, for example. With probability 1/3, his own location is chosen, and then the distance is 0. With probability 1/3, the location of agent B is chosen, and then the distance is 2. We have to cross 2 edges. And with probability 1/3, C is chosen, and then again the distance is 2. So the expected cost of each agent is 4 over 3 under the mechanism. So now let's look at the joint deviation of the 3 agents, where all of them jointly deviate to the center. And listen closely to the sound effect. Okay. So now everybody deviated to the center of the star. And so I placed everybody by this letter n, which is the set of all agents. And what happens now? So the random dictator mechanism would select the center of the star with probability 1. Right? It selects one of the agents at random. All of them are in the same place. So it would definitely select the center of the star. What's the cost of the agents after the deviation? So remember, the relocations are still here, here, and here. Right? But now the distance is only 1. The distance of each one of them to the center is only 1. So all of the agents deviated in a way that everybody benefited. Right? And therefore, the mechanism is not group strategy proof. So this is the general thing. Now, there are networks where the random dictator mechanism is, in fact, group strategy proof. So one example is on a line. Okay, but on the line, this is not really interesting, because on the line we saw that we have a perfect mechanism, the median. Right? So on the line, we can minimize the social cost and obtain group strategy proofness. So this is not really interesting. More interestingly, if the network is a circle, and we saw that on a circle the deterministic lower bound holds. So on a circle, deterministically, you can't do anything, basically. But if you take this randomized mechanism, even if the network is a circle, this mechanism is group strategy proof. And I think that I really like the proof of this theorem. So it's a very nice combinatorial proof, and you can find it in the paper that I'll mention later. Okay, so let me summarize the results that we saw so far. So we talked about minimizing the social cost. We talked about 2 types of mechanisms, deterministic mechanisms versus randomized mechanisms. And we talked about different network topologies. So we had a line, we had a tree, a circle, and we have general networks. And these are the results that we mentioned. So UB stands for upper bound, LB stands for lower bound, GSP is group strategy proof, SP is strategy proof. So if we talk about deterministic mechanisms on the line, we saw we have a perfect mechanism that's group strategy proof, the median. So we have an upper bound of 1 on the approximation ratio that you can get with a group strategy proof mechanism. And this, of course, also holds for randomized mechanisms. And we saw this also carries over to trees. So we also have the same results for a tree. On a circle, we saw that we have a lower bound of omega n for any strategy proof mechanism. So this is this. If we allow randomization, we can get a 2 approximation, which is group strategy proof. Okay, so this is this thing here. In general, the random dictator mechanism would give us a 2 approximation, but only strategy proof. On a general network, it wouldn't be group strategy proof. Now, these lower bounds are open, so we can prove a lower bound. So if you want a randomized strategy proof mechanism, you can prove that you can't do better than something like 1.03, but it's a very weak lower bound. So there's still a gap here between the lower bound of basically 1 and the upper bound of 2. So any questions about this first part of the talk? Okay, so in the second, yes, Salil.
So just the example that you presented before with the star, somehow that example wasn't too disturbing because if we have an incentive, some people have an incentive to deviate, but it only helps everybody.
Yeah.
So can you modify it so that?
Yeah, that's a good question. So basically, if you take the same example and extend the graph and put more agents on, so take build, you can start from the same thing. And and add more edges here and put a lot of agents here, and then you have the same 3 agents here. Then you can definitely build an example where the others, these 3 agents deviate and the others lose. Okay, so you can definitely extend it. Any other questions? Okay, so what I want to do in the second technical part of the talk before we move to more conceptual things is change the target function. So far we wanted to minimize the social cost, the sum of distances. I want to talk about the second target function, minimizing the maximum cost. So now the maximum cost is going to be the maximum distance between the facility and any of the agents. Okay, so instead of looking at the sum of distances, we want the maximum distance. Now, why would we be interested in the maximum distance instead of the sum of distances? For example, let's say we want to locate a fire station instead of a library. So then we would want a response time to be, we would rather our response time be 5 minutes to any of the houses in the neighborhood rather than 2 minutes to most of the houses and 20 minutes to others. Right? We don't want any houses burning down. So we want to minimize the maximum distance to any of the houses. So let's return to this simple setting where we have a line. And I want to ask, what is the optimal solution on the line? What's the point that minimizes the maximum distance? Right? So for the social cost, we saw that the median is the optimal solution. If we're interested in the maximum cost, the optimal solution is the midpoint between the leftmost reported location and the rightmost reported location. Okay, why is that? Because in that case, the cost of the solution would be, the furthest agents are in the example are A and E, the leftmost and rightmost agents. If you take any location to the left, you're getting further away from E. And if you take any location to the right, you're getting further away from A. Okay, so by moving, you only make the maximum distance greater. So the cost of this optimal solution is half the distance between A and E, or half the distance between the leftmost agent and the rightmost agent. Now here's a trivial mechanism, okay, a dictatorship of A. So whatever the agents report, I want to select the location reported by agent A. And in this setting, with respect to the maximum cost, this trivial mechanism is actually looks pretty good. So first of all, the mechanism is group strategy proof. Right? If I'm A, I don't want to lie because I get what I want. If I'm not A, I can't lie because I can't gain from lying because nobody cares what I want. Moreover, this mechanism gives a 2 approximation to the maximum cost, trivially. Right? So if I'm A, the maximum cost is the distance between A and E. Right, the distance to the rightmost agent. And then the maximum cost is this distance. The maximum cost of the optimal solution is half the distance between A and E. So the ratio between these two is 2. And in fact, this is an extreme example where A is one of the extreme agents. So if A is not the leftmost agent, the ratio would be even better. Okay, but in general, it's a trivial observation that this simple mechanism gives a ratio of 2 and is group strategy proof. Now I think much more interestingly, we have the following theorem. So if you want a deterministic strategy proof mechanism, when the agents are on a line, you can't get a ratio better than 2 for the maximum cost. Okay, so if you want to minimize the maximum cost in this setting, this trivial dictatorship mechanism is the best thing you can do. You can't do better. Okay, and that's kind of strange. Now, what I want to show you is that, once again, if we allow randomization, we can do better. Okay, so with randomization, we can push beyond this lower bound of 2. So this is a mechanism which we call the left-right middle mechanism. I think it's a very intuitive mechanism. It works as follows. So what we're going to do is we're going to choose the leftmost reported location with probability 1/4, the rightmost location with probability 1/4, and the midpoint between them with probability 1/2. So in the example, we choose A with 1/4, E with 1/4, and the midpoint between them with probability 1/2. Now, the approximation ratio for the maximum cost, so let's try to compute it. So with probability 1/2, we choose one of the extreme agents. And then the maximum cost is the distance between the two extreme agents, right? The distance between A and E, which is twice the maximum cost of the optimal solution. So with probability 1/2, I'm paying twice the optimal solution. With probability 1/2, I choose the midpoint, which is the optimal solution, right? So with probability 1/2, I get the optimal thing, and then I pay opt. And I take the ratio between this expression and opt, I get 1.5. Okay, so the approximation ratio that this mechanism gives is 1.5. Moreover, this mechanism is strategy-proof. So let me try to show this to you by extreme hand waving. So let's say that agent B is trying to improve his outcome by lying. Okay, he's trying to improve the expected distance to his relocation by lying. If he reports any location between A and E, nothing changes. The mechanism only cares about, the only input it cares about is the location of the two extreme agents. B can affect the outcome by pushing beyond the extreme agents. So for example, he can push beyond agent A. And what's happening is he's carrying the leftmost reported location with him, and he's also carrying the midpoint along with him, right? So the rightmost reported location remained the same, but he carried the midpoint and the leftmost location. Now, I want you to notice three things. First of all, it might be the case that the median got closer to B's ideal location, right? In fact, in this example, he pulled the midpoint exactly on his relocation. However, the leftmost location definitely moved away from B's relocation, right? So that's one thing. The second thing is that if B pulled the leftmost location by 2D, by distance of 2D, the midpoint moved by distance of D, right? Exactly half. And the third thing is that the probability that the leftmost location is chosen is exactly half the probability that the midpoint is chosen. So if you look at the expected cost of B, you have what he lost from the leftmost location moving away, what he gained from the midpoint getting closer, and these two terms cancel out. Okay, so it's a very simple calculation to show that B cannot gain from this lie, and this is true for any of the agents. Now, if you work a bit harder, you can show that this mechanism is in fact group strategy proof. Okay, so even a coalition of agents cannot benefit from lying. And finally, we can again show a matching lower bound. So even if you allow randomization, no randomized strategy-proof mechanism can give an approximation ratio better than 1.5 for the maximum cost on a line. Okay, so this cute intuitive mechanism is the best thing you can do with randomized mechanism for the maximum cost on a line. Questions? Tyler.
So the social cost would be higher in that case?
But we're talking about the maximum cost.
Oh, okay.
Right? So the maximum cost only depends, you only care about these two extreme agents, right? You care about the maximum distance to any of the agents. So you're talking about a situation where you have one agent here, and a lot of agents around the middle. But so if I put a facility here on the middle, right? So I still have these two agents that are stuck on the sides, and I care about the maximum distance. Right? And if I put the facility here, I'll only do worse because I'm very far from this guy. So even in this situation, the optimal solution is exactly the midpoint between the left and the right. Okay, so we once again talked about, we sort of shifted to maximum cost. We again shifted to the simpler setting on the line, and I want to again try to take it to the higher level of generalization where we're on a network. Yeah. On the midpoint, you mean, like the average. So the median. So just to show you that the median here would be very bad because it can be as bad as dictatorship, because if everybody is here and we have one guy here, the median is here, and the optimal solution is still in the middle, right? So, sorry. No, you can't be worse than it. So yeah, basically any agent that you would choose, the median is one of the agents. As long as you choose one of the agents, you get the two approximation. Right, yeah. So if I have a sub-objective, which is also the social cost, it would be better to choose the median, right? So that would give me a two approximation for the maximum cost and be optimal in terms of the social cost. Okay, so on a general network, let's again try this dictatorship thing. Okay, so again, whatever everybody reports, I want to choose the location of agent A. And this again, even on a general network, gives me a two approximation. Okay, and here the proof is trivial. So let's denote the optimal location in terms of the maximum cost by O, and X is going to be one of the agents. Now the distance between A, so we just choose the location of A. The distance between A and X is at most, by the triangle inequality, at most the distance between A and O, plus the distance between O and X. The distance between O and X is at most the optimal solution, right? It's at most the maximum distance between O and any other agent. And the same is true for the distance between A and O, which is identical to the distance between O and A. Right? So this thing is at most twice times opt, and this is true for any agent X. Right? So the distance to any agent from A is at most twice the cost of the optimal solution. And of course, the lower bound of 2 still holds on a general network. So on a general network, deterministically, still the dictator is the best you can do. So again, it's not too interesting. And for the final time, I want to show you how randomization can help us. Okay, so let's see how randomization can help us when the network is a circle. Okay, so to summarize, we're talking about the maximum cost, and the network is a circle, and we allow randomization. What can we do? I guess the first attempt would be to try to use the same left-right middle mechanism on the circle. Now, if all the agents are located on one semicircle, you can think of this as an interval on the line, in the sense that if they're on one semicircle, you know who the two extreme agents are. So you can say this guy is on one extreme, and this guy is on another extreme. So in this example, F and A are obviously the two extreme agents. So let's apply left-right middle. F would be left, and A would be right. So we take F with probability 1/4, A with probability 1/4, and the midpoint between them with probability 1/2. So what we know from before is that this would be strategy proof and would give us a 1.5 approximation if everybody is on one semicircle. If the agents are not on one semicircle, this mechanism is meaningless, right? Who are the two extreme agents? If they're sort of distributed on the entire circle, what's left and right? You can't say who the extreme agents are. So let's try another mechanism, which is much less intuitive. We call it the random midpoint mechanism. So this might seem like, where did I get this mechanism from? It's less intuitive. So first of all, let's look at the antipode and the points that are antipodal to the agent's locations. So these are the points that are diametrically opposite on the circle to the agent's reported locations. Right? So these are these blue circles here. So the random midpoint mechanism works as follows. For each pair of adjacent antipodal points, we choose the midpoint of the arc between them with probability proportional to the length of the arc. Okay, so for example, if you look at the antipodal points to A and B, the length of the arc between them is 3/8 of the circumference of the circle. So we choose the midpoint between them with probability 3/8. And the same goes for the arc between the antipodal to A and the antipodal for C. The length of this arc is 1/4 of the circumference, so we choose its midpoint, which happens to be the ideal location of A, with probability 1/4. Okay, so that's how the mechanism works, not very intuitive. So first of all, you can prove it's not completely trivial that this mechanism is strategy proof. Now here is a strange phenomenon. So if the agents are not located on one semicircle, okay, if you assume that there is no semicircle such that everybody is located on this semicircle, then this mechanism gives a 1.5 approximation, which should sound familiar. If not, if they're not if they're located on one semicircle, the approximation ratio can be as bad as almost 2. So in general, it wouldn't be better than dictatorship. But if you assume that they're not on one semicircle, it gives you again this 1.5 approximation ratio. So we have a very weird situation. We have two mechanisms. One gives us a strategy proof and gives us 1.5 approximation if the mechanisms are on one semicircle. One gives us the same guarantees if they're not. Okay, so here's a completely crazy idea. Let's just try to combine, just do the most unreasonable thing and combine these two mechanisms. So if the agents are on one semicircle, let's use LRM. If they're not, let's use random midpoint. So to anyone who has a bit of intuition about mechanism design, this thing has no chance in hell of working. It's like, the agents by lying, can shift from one mechanism to the other. So you might have a situation where they're on one semicircle. One agent lies in a way that they're no longer on one semicircle, and then you shift from LRM to random midpoint, and vice versa. And this seems like something that shouldn't ever be strategy proof. Okay, and therefore I think this, to me, this theorem was extremely surprising. So this mechanism is strategy proof. Okay, they can't gain from these lies. And it gives, of course, a 1.5 approximation for the maximum cost when the network is a circle. Now, the proof of this theorem is very technical and lengthy, but I really think the striking thing about the result is the result itself. To me, the fact that this mechanism is strategy proof it amazes me. I don't know about you, but it's pretty striking. And of course, the lower bound of 1.5 still holds on a circle. Okay, so this crazy hybrid mechanism is the best thing you can do with a randomized mechanism, a strategy-proof randomized mechanism on a circle. And one final result, so we talked about circles before we talked about trees. So if we have a tree, randomization can't help us. Okay, so on a tree, there is no randomized strategy-proof mechanism with an approximation ratio better than essentially 2 for the maximum cost. Okay, so if we have a tree, we can't do better than just choose a dictator. So let's summarize the results in this second technical part of the talk. So I don't want to go over the results. I just want to point out one interesting phenomenon. So when we talked about social cost, we saw that trees were easier than circles. Right? For a tree, we had an optimal mechanism, this generalized median. And on a circle, we had a deterministic lower bound, which was very large. And using randomization, working very hard, we were able to obtain 2. For the maximum cost, the situation is reversed. So now, with randomized mechanisms, we can get a 1.5 approximation on a circle. But for trees, we can't do better than dictatorship. We can't get better than 2. So this is a pretty strange phenomenon. For one target function, circles are easier than trees. For the other, trees are easier than circles. Okay, so just a few bibliographic notes about what we talked about so far. So these results are based on 2 papers. The first is called Approximate Mechanism Design Without Money. It's a paper with Moshe Tenlotz. It appeared in EC 2009. It contains all the results about locating a facility on the line, but most of the paper are results I didn't talk about. So I guess the most interesting part of the paper, the whole paper is location on the line. But one of the interesting extensions is locating multiple facilities. Okay, so now you want to locate 2 facilities. And the cost of an agent is its distance to the nearest facility. So you have 2 grocery stores, you just want the nearest one. Right? So that's the most interesting part of the paper, and there's another extension with multiple points per agent. So we don't have time to talk about these. The second paper is called Strategy-Proof Approximation Mechanisms for Location on Networks. It's joint work with Noga Alon, Michal Feldman, and Moshe Tenlotz. And this gives all the results about location on a network, on trees, on circles, and so on. And these 2 papers are available from my website, so just Google for Ariel Procaccia. Okay, so we basically finished the technical part of the talk. I want to give you maybe 10 minutes of a more conceptual part. Any questions, any more technical sort of questions about this technical part? Okay. So I want to introduce this agenda, which we call Approximate Mechanism Design Without Money, and see how it connects to what we talked about. And I guess the first thing I have to do is explain what algorithmic mechanism design is. So this is, I guess by now I can call it a field. There are many, many papers by now in algorithmic mechanism design. It was introduced by Noam Nissan and Amir Ronen in Stock 99. This field basically deals with designing strategy-proof, also known as incentive-compatible, approximation algorithms for game-theoretic versions of optimization problems. So this sounds exactly what we've done in this talk. But there's one very, very significant difference. Basically, all the work, and basically with no exceptions, in algorithmic mechanism design deals with designing mechanisms with money. And this is inherent in Nissan and Ronen's very definition of a mechanism. Okay, so everything assumes that you can pay the agents, that you can use the agents, you can use payments to incentivize the agents to tell the truth. Now, this assumption may be problematic in many settings, in particular the settings that are the focus of algorithmic mechanism design. For example, in internet settings, payments are very, very difficult to assume, right? You might have banking issues or security issues, so it might be very difficult to make these lots of small micropayments in order to shift and incentivize the agents. In other settings, you might have ethical considerations or legal considerations that preclude payments, for example, in political settings or kidney exchange and so on. So I think it's much more desirable to be able to obtain good guarantees without assuming that you can use payments. Okay, because the assumption is really very, very problematic, in my opinion. Now, the problems in algorithmic mechanism design, broadly speaking, fall into two classes. So the first class is the class of problems where there is an optimal strategy-proof mechanism with money, if you allow payments, but the problem is intractable. Question? Sorry. But the problem is intractable. So in principle, you could use this optimal mechanism, but you can't do it efficiently. And then you have to use approximation in order to circumvent the computational complexity of the problem, but then you lose the incentive compatibility. So the goal is to design approximation algorithms that on one hand are computationally tractable, and on the other hand are still incentive compatible, still make the payments in a way that no one wants to lie. The second class, so this first class includes problems like combinatorial auctions or scheduling on related machines, and that's the biggest class. The second class is much, much smaller. It's the class of problems where there is no optimal strategy-proof mechanism even if you allow payments. Okay, so this, for example, includes scheduling on unrelated machines. Now, the class I want to talk about is the third class that basically contains the second class and intersects the first class. And this is the class of problems where there is no optimal strategy-proof mechanism without money. Right, so this includes the second class because if there's no optimal strategy-proof mechanism with money, in particular, there is no such mechanism without money. But I want to concentrate on a specific subclass. So these are the problems where there is no strategy-proof mechanism without money, but there is an optimal strategy-proof mechanism with money, and the problem is tractable. So this new class is disjoint from class 1 and class 2. Right? For example, so it's disjoint from class 1 because the problem is tractable, and it's disjoint from class 2 because there is an optimal strategy-proof mechanism with money. Now, traditionally, people disregarded this class of problems because people said, well, the problem is tractable, we have an optimal mechanism, no problem. But once you disallow payments, once you don't want to assume that you can make payments, then this class of problems suddenly appears and gives rise to many, many interesting questions like the ones we talked about in this talk. Okay, so what we talked about falls into this class of problems that was completely disregarded before. So let me summarize a few points about approximate mechanism design without money. So first of all, like I said, and I think these are the most interesting problems, you can consider computationally tractable optimization problems. So algorithmically and traditionally, there's not a real problem here. The approximation is not used to circumvent computational complexity because the problem is tractable, but rather to obtain strategy proofness. Right? We said the optimal solution is not strategy proof. So the only way we can get strategy proofness, get truthfulness, is by resorting to an approximately optimal solution. Now, this agenda originates from previous work on incentive-compatible regression learning and classification. So the first paper about this was by Ofer Deckel, Felix Fischer, and myself in SODA 2008. And we had papers about classification in AAAI 2008 and IJCAI 2009 with Reshef Meir and Jeff Rosenchain. Okay, so this is a sort of bonus part of the talk, the last 3 slides. I want to give you a sort of advertisement of a very new paper that I think is another, in my opinion, a pretty sexy example of approximate mechanism design without money. Now, what I like about this problem is that I can explain the problem and the setting to you in 3 minutes maybe, and I can probably explain it to someone off the street in 10 minutes. Okay, so it's a very, very basic setting, but still gives rise to non-trivial problems. So let's say the agents are vertices on a directed graph. So maybe I wouldn't put it this way to a random person from the street, but to you I think I can. So the agents are vertices on a directed graph. And an edge between I and j means that agent I trusts agent j, supports agent j, votes for agent j, so choose the interpretation that you like the best. Okay, but I want to make it as general as possible. So that there's some trust or support relationship between the agents. Now our goal is to choose a subset of k best agents. And I'm going to define what best is in a minute. Now a k selection mechanism for some fixed k, so k is given from above, and we want to talk about a k selection mechanism that gets as input this directed graph and returns a k subset, a subset of size k that I denote by s. Okay, so we choose a subset of size k of the agents. Now, the utility of an agent, of agent I, for the chosen subset S is 1 if he is a part of the subset, if he was chosen, and 0 otherwise. Okay, so all agents care about are being part of this elected subset. So they're completely happy if they're a part of it, and completely unhappy if they're not a part of it. Now, the target function, so what's the set of best agents? So we want to maximize the total in degree of the agents in S. We want to maximize the total number of votes that the agents in S have. Okay, so as many votes as possible, as popular as possible. Now, the game-theoretic model is, again, we want to talk about strategy-proofness, where agents cannot benefit from lying. And the thing is that the agents are supposed to report their outgoing edges. So they're supposed to report who they vote for. And we want to design mechanisms that optimize this target function and are strategy-proof. Now, intuitively, if you think about the optimal solution, right, so just choose the subset that's best, I can benefit from lying if I hide some of my edges. So if I hide edges, I'm basically saying the other guys are getting less votes. Right? Even though I trust them or support them, I can say I don't trust anyone, and then I look better compared to the others. So here's a pretty strong impossibility result that I think might be surprising if you think about it enough. So let's take any number of agents n and any value of k. So we want to choose a subset of k agents. So k is going to be at most n minus 1. If I want... Sorry? Yeah, you can add, remove, whatever you want. So you just report any subset of outgoing edges. So let's say take any value of k at most n minus 1. If I want to select all the agents, I don't have a problem. So there's only one thing I can do. So let's say k is at most n minus 1, but any value. So the theorem says that there is no deterministic strategy-proof mechanism that gives any finite approximation ratio. I think a particularly interesting subcase of the theorem is when k equals n minus 1. So I basically want to choose everybody except one guy. I just want to throw one guy out. And then especially I'm using corollary is the following one. So Survivor is not strategy-proof. Okay, where Survivor is the popular TV show. I'm not a big fan, but I know more or less how it works. So in general, you have a stage in each show where you have this tribal council, where each member votes for each member of the tribe votes for one other member that he wants to eliminate, and then one guy gets eliminated. So let's look at a slight variation, where instead of voting for one guy to eliminate, I vote for one guy that I trust. Because I can vote for at most one guy that I trust. And again, we want to eliminate one member of the tribe. Now, the corollary that you get is the following thing. So again, my only goal in life as a player in Survivor is not to be eliminated. Right? Those who are eliminated go to this island of shame or something. It's not something you want to happen. So you don't want to be eliminated. Now, the theorem says, as a corollary, you can get the following thing. So there's no strategy-proof mechanism with the following property, the following extremely basic property. If there's just one unique guy who is the only one who got any votes, okay, it's the only one who anybody trusts, he wouldn't be the only guy who is eliminated. Right? You have to eliminate one guy. Don't eliminate the one obviously best guy. Right? So if you want this property, you can't have strategy-proofness. People would benefit from lying. So this, I guess, means that lies are inherent in Survivor in some weird sense. However, with randomization, you can do much better. Okay, so there is a randomized mechanism that gives and it's a strategy proof and gives an approximation ratio of 4 for any value of k. And as k grows larger, the approximation ratio quickly approaches 1. Okay, so it's very, very good in terms of the approximation ratio and the strategy proof. And the proof is pretty technical. So the proof of the other theorem, I think, is it's a one-page, very compact proof, very amusing. This one is very technical. Yeah, so it's a sort of random partition mechanism where you partition the agents into two groups, and you choose agents from one group based on the votes from the other group, and then you can generalize this to more groups. Sorry? Yeah, definitely. Yeah. Okay, so these results appear in a paper called "The Sum of Us: Truthful Self-Selection" with Noga Alon, Felix Fischer, and Moshe Tenmels. So to conclude, so we talked about different problems. There are many technical open problems that I think are very challenging. If you think about the facility location setting, there is an infinite number of directions for future research. So you can take this basic setting of location on the line. We talked about different extensions. So you can talk about a network. You can talk about locating several facilities. You can talk about a setting on a plane, multiple points per agents, and so on. And then you can combine any two extensions. So you can ask what happens if the agents are located on a network, but you have to locate two facilities. Okay, so there's an exponential number of directions for future research. Now, basically, this agenda of approximate mechanism design without money, so far we applied it to 4 settings. So there's the facility location setting we talked about, classification in the learning theoretic sense, subset selection, which is what I just mentioned, and there's a new matching setting that's current work with Itai Ashlagi and Moshe Tenmels. Okay, so there are 4 settings that were so far under investigation. However, I think the most interesting direction for future research is to take these ideas and apply them to other completely new settings where they would give rise to new problems and new interesting results. Thank you very much. Dimitrios.
This is all very, very good. How restrictive do you think the assumption of linearity is in the cost function?
So it's a good question. It would be completely different if you take another cost function. So for example, think about a quadratic cost function. So let's take an example. Think about a social cost and a quadratic cost function. So then if you have 2 agents, the optimal solution for the social cost would be the midpoint between them, like with the maximum cost before. So everything would be completely different. And that's, by the way, another direction for future research, other cost functions. Like I said, it's really endless. But any variation like that would be different. So look.
Related question to that. So in general, for this approximate mechanism for enough money, so it seems to be one thing that you leverage to be able to get these results is more structure that you know on the utility function.
Yeah.
Like in BCG mechanism, someone can have
Right.
arbitrary utility.
Yes.
So is that something that you think is somehow inherent for this most settings?
Yeah, I don't know. It's a good. It's a good question because so like I said, the mechanisms that I guess the pretty intuitive mechanisms that I talked about wouldn't work for other utility functions, but I really can't say if there's a general mechanism that would work for anything. So maybe if you think about facility location on the line and try to design something that takes into account the utility function, that one of the inputs would be how the utility behaves as a function of the distance, that would be cool. But I really can't say. It's not something we thought about. But it's definitely possible. You know, it's something I can't preclude. So no. So let's see. Yeah, so basically, it's a good question. I would say, yeah, I would say the same thing works. You know, so here, once you set the root, you know, you can think of any DAG as a tree once you set the root, right? It's so there wouldn't be a substantial difference.
I'm asking because it's a nice sort of basically right before you get to cycles.
Yeah.
Because there's about circles and trees. So there's also a tree generalized to DAGs. It might be feasible to extend it to general graphs by sort of decomposing it to the sort of cyclic and the DAG, the acyclic part, combine them some way. So.
Yeah. No, so basically, so I guess one thing we implicitly do is assume that the network is connected, and then it's basically a tree, right? So you know, otherwise your maximum cost would be infinite. So if you have different connected components, your maximum your distance to the agents would be infinite. So I guess it only makes sense if you talk about a tree, right? Otherwise, what's the difference? Is that okay? So basically, I guess any DAG that's connected is a tree, or can be thought of as a tree.